Okay, welcome to the class of antenna and wave propagation. Today we will discuss some fundamental parameters of the antennas, and this topics is related to the subject of antenna and wave propagation. The subject code is KEC 603. I, Mr. Himanshu Nagpal, Assistant Professor in EC Department of KGC Ghaziabad. So these are the fundamental parameters of the antennas. Means by these we can check the performance of the antenna, or we can decide the features of the antenna. First one is the radiation pattern, second is the radiation intensity, beam area, directivity and the resolution, gain, beam width, effective aperture area, antenna temperature and impedance, and there are more number of parameters which determines the or which helps in determining the features of the antenna, that is polarization, signal to noise ratio. There are number of parameters. So first of all, we will discuss the main basic parameter is the radiation pattern. This radiation pattern is generally a three-dimensional graph which helps in determining that the antenna is radiating energy in how much energy is radiating in a particular direction, or which defines the, if I say the direction, that defines that direction can be described in terms of the r, theta and phi, or you can say the spherical coordinate system. So an antenna radiation pattern is defined as the mathematical function or a graphical representation of the radiation properties of the antenna as a function of the space coordinates, so you can say the spherical coordinates. So in most cases the radiation pattern is determined in the far field region, because in the far field region the radiation pattern is generally stable and represented as a function of the directional coordinate system. If I say the antenna is placed here and this antenna radiates some energy in this direction, so the how much energy is radiated in this direction and that direction can be defined as a function of the space coordinate, and how much energy is radiated in this direction that can be described in terms of the electric field intensity, in terms of the gain, in terms of the directivity. Means this radiation pattern can also determines the some radiation properties. Radiation properties means beam width can be calculated by using the radiation pattern, directivity, gain, electric field intensity in a particular direction can also be calculated with the help of the radiation pattern. So once the electromagnetic energy leaves the antenna, the radiation pattern tells us how the energy propagates away from the antenna. So the radiation properties, radiation pattern are the three-dimensional quantity involving the variation of the field or power as a function of the spherical coordinate system, that is, you can say in terms of r, theta and phi. That r determines the observation point at which I want to calculate how much the power is radiated in this particular direction, and theta and phi determines the tells us the in which direction the antenna is radiating. So if I say this is a representation of the three-dimensional radiation pattern. Let us say these are the coordinate system, z axis, y axis and here x axis. If I say the antenna is placed here and the antenna is radiating mainly in this direction, you can say this is a two-dimensional figure, but actually it is a three-dimensional figure. Means you can say the balloon is placed here, clear, and some energy is radiated in this direction and some radiated in this direction, in this direction, in this direction. So if I want to calculate the energy at this point, let's say if I want to calculate the energy at this point the coordinate system will be, this one is the r, that is the distance between this observation point and this one, it is r, phi is the angle between this one, that is phi, and theta is the angle between this one. This is theta this is phi. If I want to place this, you can say here, let me erase some points. Theta x. Now, if I want to calculate, so take the transformation at this plane. So you can say this one is the phi, theta is this angle at this point, theta is this angle, and this one is the r. Clear? So above figure shows that the three-dimensional field pattern with a pattern radius r is proportional to the field intensity in the direction of the theta and phi. So one of the example of the radiation pattern is this one. Let's say this is a antenna, that is a dipole antenna, and the current is provided to this dipole antenna, and the radiation pattern of this dipole antenna is like this one. Means this dipole radiates its energy in this whole direction, like this one. This is a three-dimensional radiation pattern, and you can see there is a null at this point, and this means the shape of the apple. Or you can say the antenna is radiating in this direction. So for an antenna, the radiation pattern can be described in terms of the field pattern, power pattern, and this radiation pattern can be described in terms of three types, or there are number of types also: field pattern, power pattern, and the power pattern in decibel, power pattern in the linear scale. This power pattern represents in linear scale represents the square of the magnitude of the electric field intensity of magnetic field as a function of the angular space, that is theta and phi, and the power pattern represents the magnitude of the electric field or magnetic field, or you can see the magnitude of the power in decibel as a function of the angular space, and the field pattern represents the plot of the magnitude of the electric field magnetic field as a function of the angular space. Let's say take an example, this one. This is a linear scale. If I want to calculate the power pattern in dB scale. Let's say, first of all, now let me take this one. This one. If I want to show this radiation pattern in the two-dimensional as a two-dimensional figure, so this radiation pattern can be determined as this one, like this one. Means if I say this is a major power radiated in this direction, that represents this one, and these are some lobes where the power is less as compared to the power in this direction, and in two dimensional these can be represented as like this one. So this is generally known as the major lobe, means maximum power is in this direction, that is known as the major lobe, and the rest of the known as the minor lobes. And minor lobes, further there are two categories. This one is the back lobe, the opposite to the major lobe, that is known as the back lobe, and these are known as the side lobes, and rest are known as the minor lobes. So like this one. Now see, first term will discuss, that is the normalized field pattern. This normalized field pattern, if I want to calculate the normalized field pattern, normalized of anything, the calculated field is to be divided by the maximum field that defines the normalized field pattern. Let's say if I want to calculate the normalized field pattern at this point, clear? So if I want to calculate the normalized field pattern at this point, so the electric field at this point is E theta divided by the maximum field of this slope, E theta phi in the maximum. So that defines the normalized field pattern. Similarly, if I want to calculate normalized power pattern, this means the power, normalized power in particular direction divided by the maximum power in that particular direction. So next term, next parameter which can be calculated using a radiation pattern is the beam width. So angular separation between the two half power point is known as the half power beam width, and the angular separation between the first two nulls is known as the beam width between the first nulls. Let's say in the next figure we will discuss about the field pattern, power pattern linear scale, and the power pattern the decibel scale, and we will also discuss about the beam width of half power beam width and the. Now see, first discuss about the field pattern. If I say this is a radiation pattern of an antenna, as it describes the field pattern, it means this shows the electric field in this direction. If I say this theta at this point, theta is equal to 0 degree, clear? Now if I say the maximum field, normalized field will be equal to what? 1, because maximum divided by maximum, that defines the equal to 1. Normalized field pattern will be equal to 1, and now this represents the electric field, that is why it is known as the field pattern. If I say this is a power pattern, that determines the normalized power in this particular direction and in decibel scale, means milliwatt or microwatt, anything, clear? And field pattern decibel scale means this represents the normalized power pattern theta comma phi, clear, in unit of decibel, clear? So this is the difference between the field pattern, power pattern, and the power pattern, the decibel scale. Both have a same type of radiation, but their unit is changed. This shows the field in this direction, this graph shows the power in this direction, this graph shows the normalized power in this direction, that is in the decibel. So now calculate the half power beam width and the first null beam width. So in field pattern, the half power beam width, the power where the point where the field gets where the power gets halved, the angular separation between that points is known as the half power beam width. But if I say in terms of electric field, then that is known as the 1 by root 2 of the that one. That means if I say this is having a point, maximum point is 1, having a magnitude 1, so 1 by root 2 of that is equal to 0.707. So there is some point at which it comes out 0.707, and there is, if I say goes like this one, there is some point at 0.707. The angular separation, now the antenna is placed here, the angular separation between these 2 points, that defines the half power beam width, clear? If I say the balloon is here, and if I say the balloon is like this one. So if I say this is a maximum point, the point at which it is 0.707, and from this point at this point, the angle between these two, that defines the half power beam width. And the angular separation means this is a major lobe and this is a second lobe. Second we have minor lobe. First minor lobe adjacent to this one. So angular separation between these 2 points, that defines the first null beam width. Generally we can say the first null beam width is twice of the half power beam width. Now see, how can we calculate the half power beam width and the first null beam width in this power pattern or in linear scale? If I say the maximum power, normalized maximum power is 1 in this direction, that is this direction, so there will be some point at which the power, if I say the balloon is like this one, there is some point the power gets halved, means let us say at this point power gets halved, that is 0.5 of this one, or you can say half of this maximum normalized, and that is 0.5. And if I say like this one, that's the point for the angular separation between these two, that defines the half power beam width. And this half power beam width consists of both components, that is theta and the phi. And the angular separation between these, this is a major lobe, then this is a second lobe adjacent to the major lobe. And that is the angle, there is a null between these two. This is a first null, and from this side there is a first null. The angular separation between these two nulls, that defines the first null beam width. Clear? Now from the power pattern decibel scale, if I say this power, a normalized power is maximum in this direction, that means the magnitude will be equal to 1. Now 20, how can we say that is in decibel, means 10 log of 1, means 10 log of 1, that is equal to 0 dB. So this will be point, that is where it is 0 dB. Clear? Now see, if I say this is a 0 dB, 0.5 of, means the half power beam width is 0.5 of the maximum, half of the maximum. Now if I say half of the maximum, it is 1/2 of, means if I say that is there will be some point will be a 0.5, and that 0.5 is the 10 log of 1/2. Clear? And that will be equal to -3. So the point where it is -3 dB and here it is -3 dB. So angular separation between these two defines the half power beam width. Clear? And this is the angular separation between these two nulls, first null of right hand side, first null between this left hand side, that defines the first null beam width. Clear? Now next one is the radiation pattern lobes. From the radiation pattern we can determine the how much power is radiating in this direction, in that direction. So if I say this is a radiation pattern, so maximum power which is radiating in this direction, that is known as the major lobe, and rest these are known as what? Minor lobes. And these minor lobes is further categorized into two types, that is the side lobes and the back lobe. The exact opposite to the major lobe, that is known as the back lobe. And adjacent to the major lobe, these are known as the side lobes, and rest are known as the minor lobes. So from the radiation pattern we can also determine the which type of antenna is this one. ठीक है. Or you can say the radiation from the radiation pattern. From the radiation pattern, there are three types of radiation patterns are there, or number of radiation pattern, but we will mainly discuss that is the isotropic radiation pattern, isotropic radiation pattern of antenna, directional radiation pattern of antenna, and omnidirectional radiation pattern of antenna. Radiation pattern of so isotropic radiation pattern is defined as the antenna which radiates energy equal in all direction with equal intensity at a particular direction in a particular spherical radius of sphere. Let's say a balloon of shape in the all over in the same means, like if I say circle and the antenna is placed here, if this circle is uniform means it provides the radiation, in all the direction with equal intensity. So that type of radiation pattern is known as the isotropic radiation pattern. And another is the directional radiation pattern. This is a directional radiation pattern like this one, which I have already given you, like this one. Means it radiates energy, some energy in the maximum in the some direction and some amount of energy in another direction. Means the radiation means the power which is getting radiated, maximum power, some maximum power amount of radiated in some particular direction, another amount of power radiated in some other direction. So that type of radiation pattern is the directional radiation pattern, or that type of antenna is known as the directional antenna. The antenna which radiates or receives electromagnetic energy more effectively in some direction as compared to the other. Omnidirectional antenna, and omnidirectional is antenna radiation pattern is a special type of antenna or special type of directional antenna. For example, like this one, figure of 8, you can see figure of shape of apple. The radiation pattern can be like this one. It is somewhat like radiates energy in all the direction, but there is some null point in which energy will not be radiated, like this one. If I say this is an apple like this one, or you can say there is like this one, means it radiates there is some null point at this direction and some null point in this direction. So that type of antenna is known as a special type of antenna of directional type pattern, that is a omnidirectional antenna. So next term is the radian and steradian. In the plane, if I said in the two-dimensional figure, the measure of the plane angle is known as a radian, or you can say in the terms of degree also. But if I say three-dimensional figure, for the three-dimensional figure, or you can say example like balloon, the angle between these two in the balloon, that is a three-dimensional figure, and the unit of that is known as the solid angle. That is not a plane angle, that is a solid angle, and that solid angle is measurement of that solid angle in terms of steradian, that is known as the steradian. So you can see here that this is a circle. In circle, one radian is equal to like this one. That is the, if I say this is angle theta, theta equal to L by R. This theta equal to 1 radian when length of arc is equal to when length of arc is equal to the radius. ठीक है? That means L by R equal to R by R, that is equal to 1 radian. So you can see here the definition that the 1 radian is defined as the plane angle with its vertex at the center of circle of radius R that is subtended by an angle whose length of arc is R. And similarly, if I say this is a sphere, so steradian is this is a solid angle. The solid angle which is in this direction, that is a solid angle, and this solid angle unit of solid angle is in the steradian, and this 1 steradian is equal to 1. If I say it covers the area of equal to R square, means area is equal to R into R. When it covers the area of R into R, that defines the one solid angle, that defines the solid angle of 1 steradian. Clear? If I say whole sphere consists of how many steradian? If you know that the surface area of whole sphere is equal to 4 pi R square and 1 steradian covers the R square, it means the whole sphere consists of what? 4 pi steradian, and the unit of steradian is represented as SR. Clear? So the whole sphere consists of 4 pi steradian. So till today I have discussed the topic, that is the radiation pattern of the antenna, and from the radiation pattern we have calculated how can we calculate the beam width and the major lobe, minor lobes. I have discussed, and I have discussed the term that is a radian and steradian. In the next lecture, we'll discuss about the another fundamental parameters of the antennas. The book which I have referred for preparing these slides is the Antennas by the J.D. Cross, and the Antenna Theory and Analysis and Design by the C.A. Balanis, and the another one is the Antenna and Wave Propagation by the K.D. Prasad Satyaprakashan, 3rd edition. Thank you.